What if the Big Bang wasn't the birth of everything, but just a transition? What if reality existed calmly long before time itself ever started ticking? Before we dive into this topic, make sure to subscribe and comment where in the world you're watching from. Most of us grew up with a very specific image of the Big Bang burned into our minds. A tiny dot, absolute nothingness. Then suddenly, boom, everything explodes outward and the universe is born. Space, time, matter, energy, all bursting into existence from literally nothing at all. It's clean, it's dramatic, and it fits nicely into a school textbook or a 5-minute animation. The problem is that this story, while useful for beginners, is deeply misleading. Modern physicists do not actually work with this cartoon version of the universe. They tolerate it as a teaching tool, but they don't believe it in a literal sense, because when you look closely, the phrase "everything came from nothing" isn't just confusing, it's physically meaningless. In physics, nothing is not a thing you can point to. It has no equations, no measurable properties, no rules, and science only works when rules exist. The simplified story also quietly hides a major issue. If the Big Bang truly began from absolute nothingness, then the laws of physics themselves would have had to appear out of nowhere fully formed. Gravity, quantum mechanics, relativity, all spontaneously popping into existence without cause. That isn't an explanation, it's a philosophical placeholder. What actually happened in cosmology classrooms over the decades is subtle but important. The Big Bang theory was never meant to explain the ultimate origin of reality. It was designed to describe the early evolution of the universe once it was already hot, dense, and expanding. Somewhere along the way, that distinction got lost. The model explained the aftermath so well that people assumed it also explained the beginning. Even the word bang is a trap. It wasn't an explosion in space. There was no center, no debris flying outward into emptiness. Space itself was expanding, every point moving away from every other point simultaneously. That alone already breaks the mental picture most people carry. So when physicists say the Big Bang happened, what they really mean is something far more specific and far less mystical. They mean the universe passed through an extremely hot, dense phase and then expanded and cooled. That's it. No claim about absolute beginnings, no claim about nothingness, no claim about what came before. And that gap between what the theory actually says and what we were told it says is where the real mystery begins. The moment someone asks, "What happened before the Big Bang?" you can almost feel the resistance in the room. Physicists shift uncomfortably. Teachers wave it away. Popular science books shut the question down with a single sentence: "There was no before. Time itself began at the Big Bang," they say, so the question is meaningless. Like asking what's north of the North Pole. Case closed, except it isn't. That answer sounds confident, but it's built on a very fragile assumption that our current description of time remains valid all the way down to the earliest possible moment. And that assumption is precisely where modern physics starts to break. General relativity tells us that space and time are dynamical. They stretch, curve, and respond to energy. Under extreme conditions, they can even tear. When you mathematically rewind the universe using Einstein's equations, time doesn't gently fade away. It violently collapses. The equations spit out infinities. Densities become infinite. Curvature blows up. Time as a concept stops making sense not because it truly ends, but because the theory itself has stopped working. That distinction matters. When physicists say time began at the Big Bang, what they often mean is our equations cannot describe anything earlier. Those are not the same statement. One is a claim about reality. The other is a confession of ignorance. Quantum physics quietly makes this even more uncomfortable. At very small scales, time behaves nothing like the smooth river we experience. It becomes fuzzy, probabilistic, potentially emergent rather than fundamental. Some approaches to quantum gravity don't even include time as a basic ingredient at all. It arises later, the way temperature structure emerges from the motion of atoms. If that's true, then insisting that time must have a sharp beginning may be completely backwards. This is why the illegal question argument doesn't hold up under scrutiny. Asking what came before the Big Bang isn't forbidden by nature. It's forbidden by outdated intuition. The laws we trust most are being pushed beyond their domain of validity, and instead of admitting that, we pretend the question itself is the problem. But history shows this pattern over and over. Whenever physics declares something unaskable, it's usually standing at the edge of a deeper theory. Time didn't necessarily break at the Big Bang. Our description of it did. And once you accept that, the door to what came before quietly reopens. Einstein never set out to explain the birth of the universe. In fact, when he finished general relativity in 1915, the idea that the cosmos might have a beginning wasn't even on the table. What he built was something far more subtle and far more dangerous to our intuition. He gave physics a set of equations that didn't just describe gravity, but made space and time themselves dynamic, responsive, and fragile. Those equations carry a quiet warning that often gets overlooked. When applied to the universe as a whole, general relativity doesn't naturally allow for a calm, eternal cosmos. The mathematics insists on motion, expansion, or collapse, a universe that evolves. And when you push those equations backward toward higher and higher densities, something deeply unsettling happens. The theory predicts its own breakdown, not gently, but catastrophically. This is where singularities enter the story. A singularity is not a physical object. It's a signal flare from the mathematics saying, I can't go further. Infinite density, infinite curvature, time coming to a halt. On paper, this looks like a beginning, but to a physicist, it's a red flag. Infinities are not features of reality, they are symptoms of an incomplete theory. Einstein understood this instinctively. He never liked singularities. He didn't see them as real places where physics ends, but as indicators that something essential was missing from the equations. In private letters and conversations, he repeatedly expressed discomfort with the idea that nature would allow such pathological behavior. A universe that begins with infinities is not elegant, it's broken. Later, Hawking and Penrose proved that under reasonable assumptions, general relativity predicts singularities are unavoidable. But even they were careful about what that meant. The theorems don't prove that a singularity exists in nature. They prove that general relativity cannot remain valid under extreme conditions. And this is the silent warning embedded in Einstein's theory. If the laws of physics predict a beginning that destroys the laws themselves, then that beginning cannot be the final word. A true origin that annihilates causality, time, and predictability is not a foundation, it's a boundary marker. General relativity doesn't so much announce the beginning of everything as it whispers that it cannot describe it, and that whisper is the first clue that the universe's story didn't start with a clean, absolute beginning at all. At first glance, nothing seems like the simplest concept imaginable. No matter, no energy, no space, no time, just absence. But the moment physics gets involved, that clean idea collapses almost instantly, because in modern physics, nothing refuses to stay empty. Quantum mechanics dismantles the classical notion of a void at a fundamental level. Even when you remove every particle, every atom, every photon, you are still left with fields, invisible, pervasive quantum fields that exist everywhere in space. These fields cannot be turned off. They are not optional features of reality, they are the stage itself, and those fields are restless. Thanks to the uncertainty principle, energy can never be perfectly zero. If it were, the system would have an exact value, which quantum mechanics forbids. As a result, empty space seethes with activity. Particle pairs constantly pop into existence and annihilate each other almost instantly. These aren't metaphors, they are measurable effects. We see them in experiments. We calculate them precisely. They influence forces, masses, and even the structure of atoms. So when someone says the universe came from nothing, the question immediately becomes which nothing? Because the nothing allowed by quantum physics is anything but inert. It has structure, It has energy. It obeys laws. In fact, it may be the most powerful thing in existence. The vacuum is not an absence of reality. It is a dynamic medium with enormous potential. This creates a deep conceptual shift. If empty space already contains energy, then creating a universe doesn't require conjuring something from absolute non-existence. It requires a transformation, a rearrangement, a release. The real mystery moves from why is there something instead of nothing to why does the vacuum have the properties it does. Even more unsettling is that true nothingness may be impossible in principle. To have absolutely nothing, you would need to remove the laws of physics themselves, but without laws, the concept of nothing becomes meaningless. There is no framework left to define absence. This is why many physicists no longer treat nothing as the starting point. It's not stable. It's not empty, and it's certainly not simple. The universe doesn't appear to have emerged from a featureless void. It appears to have emerged from a state rich with hidden structure, governed by deep rules we are only beginning to understand. And once you accept that, the idea of a universe appearing from nothing stops sounding profound and starts sounding like a misunderstanding. Once physicists accepted that empty space isn't truly empty, an even more unsettling realization followed. That restless quantum vacuum doesn't just flicker with temporary particles, it carries energy, enormous energy, and this single fact quietly rewrites the entire story of how universes can begin. In quantum field theory, every field has a lowest possible energy state, called its vacuum state, but lowest does not mean zero, it means the minimum allowed by the rules of quantum mechanics. Even in perfect emptiness, fields still vibrate. Those vibrations add up, and when you calculate how much energy should be stored in empty space, the number you get is absurdly large, far larger than anything we observe directly. For a long time, physicists tried to ignore this. The mismatch between predicted vacuum energy and observed cosmic energy is the worst theoretical error in all of science, off by more than 100 orders of magnitude. But ignoring it doesn't make it go away, because gravity feels energy, all energy, and vacuum energy gravitates. Einstein stumbled onto this idea long before quantum theory was complete. His cosmological constant was essentially vacuum energy written into space-time itself. He introduced it reluctantly, removed it later, and then watched history circle back. Today, we know the universe's expansion is accelerating, driven by something eerily similar to what Einstein once tried to erase. Empty space is pushing the universe apart. This is where cosmic origins take a dramatic turn. If empty space contains energy, then a universe does not need matter or radiation to exist at first. It can begin as pure geometry, expanding space powered by vacuum energy alone. No particles, no light, no heat, just expansion. That changes the Big Bang from a creation event into a conversion event. The hot, dense universe we see evidence for may not be the start of existence, but the moment when vacuum energy transformed into matter and radiation. A phase change, not an absolute birth. Hidden inside empty space is the capacity to create entire realities, galaxies, time, structure. Observers asking questions like this one, and once you accept that the vacuum is not passive but generative, the origin of the universe stops looking like a miracle and starts looking like a natural consequence of deeper laws we're only beginning to glimpse. For a while, the Big Bang looked unstoppable. Every new discovery seemed to strengthen it. The cosmic microwave background, the abundance of light elements, the expansion of space itself. But beneath the surface, something was deeply wrong. The theory worked astonishingly well, almost too well, except for a few details that made no physical sense at all. The universe was suspiciously smooth, too uniform. Regions on opposite sides of the sky had the same temperature despite having no time to communicate. Space was balanced on a knife edge between expansion and collapse. Exotic particles predicted by high-energy physics were nowhere to be found. These weren't minor flaws, they were structural cracks. Then came a shift in perspective that changed everything. Instead of asking what happened at the Big Bang, a small group of physicists began asking what happened just before it. And that single change of framing opened the door to inflation. Not a tweak, not a patch, a complete rewrite of the opening chapter of cosmic history. The idea was radical in its simplicity. The early universe wasn't dominated by matter or radiation at all. It was dominated by vacuum energy, a strange, unstable state of space itself that caused expansion to go berserk. Not gradual growth, exponential growth. In a fraction of a second, space expanded by an unimaginable factor, stretching any initial curvature, smoothing out irregularities, and separating regions that were once tightly connected. What we call the Big Bang, the hot, dense fireball, wasn't the beginning. It was the ending of this inflationary phase. When inflation stopped, its energy didn't disappear. It transformed. Space dumped its stored energy into particles, radiation, and heat. The universe suddenly became filled with matter. Temperature skyrocketed, nuclear reactions ignited. That familiar Big Bang story finally begins, but only after something far stranger had already happened. This realization flipped the narrative upside down. The bang wasn't a creation event, it was a consequence, a transition, the aftershock of a deeper process operating at scales beyond everyday intuition. Inflation didn't just fix mathematical problems, it reframed the question entirely. The universe didn't explode into existence. It emerged from an earlier phase governed by rules we're still uncovering, and once that door opened, it became impossible to pretend the story started where we were taught it did. The popular image of the universe's birth is loud, violent and chaotic, a colossal explosion ripping reality apart, matter flying outward in every direction, space tearing itself open in a single deafening instant. It's cinematic, it feels intuitive, and it's almost certainly wrong. Inflation replaces that violence with something far stranger and far quieter. According to the inflationary picture, the universe did not begin in a state of chaos at all. It began in an eerily smooth, almost featureless condition. No galaxies, no particles, no radiation, just space itself, expanding calmly but unimaginably fast, driven by vacuum energy. There was no fireball, no shockwave, no center of detonation. In fact, there wasn't even anything that could meaningfully be called stuff. This is deeply counterintuitive because we associate creation with noise and destruction. But physics doesn't care about our instincts. The equations point to a beginning that was astonishingly ordered, uniform, symmetric, nearly perfect. During inflation, space didn't need matter to expand. It didn't need temperature or pressure. Expansion was built into the fabric itself. Every tiny region was smoothed out as space stretched, erasing imperfections the way wrinkles disappear when a surface is pulled tight. What chaos existed beforehand, if any, was diluted beyond recognition. The irony is that all the complexity we see today came from this calm beginning. The galaxies, the clusters, the vast cosmic web, they didn't emerge because the universe was turbulent at birth. They emerged because it was almost too uniform. Tiny quantum fluctuations, microscopic variations that inflation stretched to cosmic scales, became the only imperfections left. Gravity did the rest over billions of years. So the universe wasn't born screaming. It whispered. The heat, the radiation, the nuclear reactions, all of that came later when inflation ended and its stored energy converted into matter. What we call the Big Bang was not the moment of maximum chaos, but the moment order transformed into complexity. This idea overturns one of our deepest assumptions. Creation did not begin with destruction. It began with stability so extreme that even the smallest disturbances became the seeds of everything, and that calm origin may be the most unsettling part of the story because it suggests the universe didn't fight its way into existence, it simply unfolded. Once inflation entered the picture, it refused to stay small. The mathematics that made inflation work so beautifully carried an unexpected consequence, one that physicists didn't ask for but couldn't ignore. Inflation doesn't like to stop. Not everywhere, not all at once. This is where Michio Kaku's perspective becomes especially unsettling. In many inflationary models, the inflation field decays randomly. In some regions of space, it loses energy and converts into matter and radiation. That conversion event is what we experience as a Big Bang. But elsewhere, inflation keeps going. Space continues to expand exponentially faster than any decay process can shut it down. The result is a strange cosmic hierarchy, isolated pockets where inflation ends, embedded inside an ever-expanding background where inflation never stops. Our universe may be one of those pockets. From the inside, it looks like a complete cosmos with its own space, time, particles, and physical laws. From the outside, if outside even makes sense, it's just a bubble in a much larger inflating reality. New bubbles continue to form, old ones drift apart faster than light can ever reconnect them. There is no global beginning, no single creation event, just an ongoing process. This is eternal inflation. In this view, the Big Bang was not the start of everything. It was the start of our region, a local event in a much grander structure that has no clear origin in time. Reality didn't switch on once. It's been reproducing itself continuously. What makes this idea especially uncomfortable is how naturally it emerges. Eternal inflation isn't added for drama. It falls out of the equations when physicists try to make inflation consistent with quantum mechanics. Once randomness enters the picture, inflation becomes self-sustaining. Kaku often emphasizes the philosophical weight of this shift. If universes are constantly being born, then ours is not special because it exists, but because it has the right conditions to allow complexity, chemistry, and observers. The laws we measure may not be universal truths, but local bylaws of our cosmic neighborhood. This reframes existence itself. The question stops being why does the universe exist and becomes why do we exist in this universe? And in that subtle shift, the Big Bang shrinks from a cosmic genesis into something far more unsettling, a regional event in an endless inflating reality that may never have begun at all. The multiverse is one of those ideas that makes even seasoned physicists uneasy, not because it's mystical or poetic, but because it threatens the very foundation of how science normally works. Physics is built on prediction, testability, and falsification, and the multiverse sits right at the edge of all three. The discomfort starts with a simple issue. If there are countless universes beyond our own, separated by distances that can never be crossed or observed, how do you test that claim? You can't point a telescope at another universe. You can't run an experiment inside one. To many physicists, that sounds dangerously close to stepping outside science altogether. And yet, here's the problem. The multiverse wasn't invented to be provocative. It wasn't introduced to solve philosophical puzzles or to comfort existential questions. It emerged because physicists were trying to make their equations honest. Inflation works frighteningly well. Quantum mechanics works frighteningly well. When you combine them, eternal inflation and multiple universes fall out almost automatically. Removing the multiverse often requires unnatural fine-tuning, forcing the math to behave in ways it doesn't want to. In that sense, the multiverse isn't an extra assumption. Avoiding it is. This creates a deep tension. On one hand, physicists don't like theories that can't be directly tested. On the other hand, they like theories that don't collapse under their own logic. The multiverse sits exactly at that crossroads. There's also a psychological resistance. If physical laws vary from universe to universe, then the constants we measure, the strength of gravity, the mass of particles, the structure of space, may not have deep fundamental explanations. They may simply be environmental. That idea feels unsatisfying. It replaces inevitability with contingency, elegance with selection. But nature has never promised to be emotionally satisfying. Some physicists argue that indirect evidence could exist, subtle imprints in the cosmic microwave background, statistical predictions about which kinds of universes can host observers, patterns that would be extremely unlikely in a single universe model. None of this is settled, but it's not empty speculation either. The multiverse scares physicists because it challenges control. It challenges uniqueness. It challenges the idea that the universe had to be the way it is. But fear alone isn't a scientific argument. If our best theories keep pointing in the same unsettling direction, ignoring them doesn't make them go away. The multiverse may be uncomfortable, it may be incomplete, it may be hard to test, but that doesn't mean it's optional. It may simply be what reality looks like when we finally stop insisting that it be simple. At first, all of this can feel distant, abstract, galaxies, inflation fields, multiverses, ideas so large they seem disconnected from everyday life. But redefining the beginning of the universe doesn't just rewrite a textbook, it quietly rewires how you fit into reality. If the Big Bang was not the absolute beginning, then existence is not a fragile accident balanced on a single explosive moment. The universe is not a one-time miracle hanging over nothingness. It is part of a deeper process, stable enough to generate structure, complexity, and observers again and again. That alone changes the emotional tone of existence. Reality becomes less brittle, less temporary, less absurd. It also reframes meaning. If our universe emerged from laws that existed before time as we know it, then you are not the byproduct of chaos. You are the outcome of deep, persistent order. The same quantum fluctuations that shaped galaxies are written into your atoms. The same vacuum energy that expanded space made chemistry possible. Your existence is not separate from cosmic history, it is a continuation of it. There's humility in this picture, but also responsibility. If our universe is one bubble among many, then what makes it special isn't its existence, but its capacity for awareness. Stars don't care that they exist. Galaxies don't wonder where they came from. You do. And that makes consciousness one of the rarest phenomena in the entire cosmic process. This perspective also dissolves the fear of asking big questions. If the universe didn't begin from nothing, then curiosity itself is not a mistake. Wonder is not a glitch in an indifferent cosmos. It is what naturally emerges when matter becomes complex enough to look back at its origins. You are living inside a universe that remembers its past imperfectly, investigates its own birth, and slowly learns the rules that made it possible. Redefining the beginning doesn't shrink you, it places you inside a much larger story, one that didn't start with a bang and didn't end with you asking these questions. And that may be the most profound shift of all, realizing that understanding the universe is not separate from being part of it. If this changed the way you think about the universe, don't let the curiosity stop here. Subscribe, like the video, and step with us deeper into the mysteries of reality, because the more we learn, the stranger and more beautiful the universe becomes.